Okay, so we're in chapter 2, section 1. And if I were to have an equation a y double prime plus b y prime plus cy is equal to 0. If I had some equation that looked like that, and I were to guess that my solution was y is equal to e to the rx, if I were to do that, then I could say y prime is r e to the rx, and y double prime is r squared e to the rx. I could do that, and then I could substitute that back into my equation and say that a r squared e to the rx plus b r e to the rx plus c e to the rx is equal to 0. Now, can I divide by 0? No, can't divide by 0. Okay, so, but is e to the rx ever 0? E to the rx does something like this, right? And it's always going to be okay, so I can divide by e to the rx. So I can have a r squared plus b r plus c is equal to 0. And then what am I looking at? Well, it looks to me like I have a quadratic formula, right? And if I have a quadratic formula, what can you tell me about its roots, the roots of a quadratic formula? There's 3 possibilities for the roots of a quadratic formula. So I could have R1, R2, that'd be my case 1. Case 1, R2, I have 2 distinct roots. That's a possibility, right? Or case 2, I could have another possibility. What's case 2? I could have the same root, R and R, right? And what's the third possibility? All right, so my third case is, case 3, I could have alpha plus or minus beta I. Okay, because when I have a quadratic formula, I've got that R is going to be minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? And depending on what's in that square root guy will either give me 2 distinct roots, the same root repeated, or an imaginary number root. Those are my abilities. All right, so if I have a quadratic formula, no matter what it is, if I have something that looks like this, I don't necessarily have to know what it is, but it is going to end up having a characteristic equation. And the characteristic equation is going to look like that. I'm going to keep my coefficients that are numbers. I'm going to put in an r or an m. You could use an m if you want to do that. I'm going to square it if it's a second derivative. I'm going to have a unit guy if it's first derivative, y to the 0, which I don't write down, if it doesn't have any derivatives. And with that characteristic equation, I'm going to find the roots. And if the roots are distinct, if that's the case, then my answer to the equation becomes C1 e to the R1x plus C2 e to the R2x. And that's the answer to my differential equation, second order. If I have the same root, so I have the same root, then I end up with y is equal to C1 R1x there's no R1, it's just R, plus C2x e to the Rx. So I need to have, a second order differential equation needs to have two separate orthogonal to each other. They're not. So I end up having to add an x in there if I have two of them. If I have an imaginary number as my answer, then my answer becomes y is going to be e to the alpha x times cosine C1, C1 cosine x plus C2 sine x. So now, if I have a differential equation that only has numbers for their coefficients, and they're not y of x or an x squared or something weird like that, then I can find the characteristic equation, use the characteristic equation, solve that differential equation. So now the next issue on our plate is how do we know something is linearly linearly independent? So if I have a 1 and I have a 2, are they linearly independent? Yeah, because I can multiply 2 by the 1. If I have an a, some constant, and I have an x, are they linearly independent? Yeah, they are. So if I look here and I see here's my a and here's my x, they're linearly independent of each other. Right? No matter what I do, I can't turn the a by multiplying. How about x and x squared? Are they linearly independent? Yeah. How about sine and cosine? Are they linearly independent? Okay. How about e to the x and e to the 2x? They linearly independent? No way I can multiply this guy by some constant. How about hyperbolic sine of x and e to the x? They're linearly independent? All right, so hyperbolic sine, hyperbolic cosine, hyperbolic sine, e to the x minus e to the minus x over 2. Hyperbolic cosine, e to the x plus e to the minus x over 2. What's the derivative of the hyperbolic cosine? What's the derivative of hyperbolic sine? Hyperbolic cosine, right? What's the derivative of hyperbolic cosine? Hyperbolic sine. Okay. So your sines and cosines are circular functions. You go sine. Same thing is true of the hyperbolic sine and hyperbolic cosine. They go back to each other too. So the hyperbolic sine and the hyperbolic cosine are in fact linearly independent, but they're not linearly independent to yes because they have yes. Okay. So that begs the issue of how do we know something is linearly independent? And the answer is we take the Wronski, R-O-N, WRON. Oh, I got that far right. SK. We take the Wronskian of the function. Okay, so, and if the Wronskian of the function is not equal to 0, then we are linearly independent. Linearly independent. And if the Wronskian is equal to 0, then we are linearly dependent. Okay, so, and the way I take the Wronskian, let's say I got f of x, and I got g of x, that doesn't work, and I have an h of x, and I want to know whether or not they are linearly independent. What I'm going to do is I'm going to take the Wronskian of f, g, and h, which is the determinant of f of x, f prime of x, f double prime of x, g of x, g prime of x, g double prime of x, h of x, h prime of x, h double prime of x. If I could spell it right. And if that guy is not equal to 0, I'm linearly independent. If he's equal to 0, I'm linearly. All right, so we'll practice doing that. And I could have 4 of them, I could have 5 of them. It doesn't matter how many functions I have. If I have 5 of them, then my determinants of 5 by 5 guy. It's going to take me the rest of the day to solve it. But other than that, it's not a real issue. So we'll look at sine x and cosine x. And our first thought is they are linearly independent, as we said already. If I take the Wronskian of those guys, I'm going to have sine x, cosine x, minus sine x. And so I got minus sine x squared minus cosine squared. If I put the square in the right spot. Sine squared x, which becomes minus 1, which means these guys are linearly. If we do it again, 2 and 3. Okay, so the Wronskian of 2 and 3, 2, 0, 3, 0, equals 0. So 2 and 3 are not. How about x? How about 2x and 3x? Okay, so we got 2x, we got 2, we have 3x, we have 3, and we have 6x minus 6x, 0. 2x and 3x are not linearly independent. Okay. And clearly, why are we discussing Wronskians at all, otherwise other than republish? Because we're going to use it someplace in the future. Problems. 1 through 49. 1 through 49 and 1 through 25. Okay, so that's section 1. Hope there's not much in section 2. So we've got to do section 1 problems and then do section 2. All right, so I'm going to do problem number 2. And y double prime minus 9y is 0. Y1 and Y2. Y at 0. know what we're supposed to do yet? Homogeneous second order integrated two functions all over initial equations. First, verify that y1 and y2 are solutions. Okay, so that's what we're going to do. So we're going to look at y1 is e to the 3x, y prime 1 is 3e to the 3x, y double prime 1 is 9e to the 3x. If I take 1, minus 9 of those, and 1 of these guys, I would do that, which the equation says, I'm supposed to get 0. Okay, so minus 9 plus 9 is 0, check. So the first guy is in fact a solution to the equation. Notice I'm doing this in a vertical manner. I'm doing it on purpose. Oh, excellent. All right, now we're going to check the other guy. y2 e to the minus 3x, y2 prime minus 3e to the minus 3x, y double prime to 9e to the minus 3x. If I take one of these guys and minus 9 of those guys, I'm supposed to get 0. And 9 minus 9 is 0, so it checks. So now, if I'm given the solution to a problem, I can check it. Okay, well, that's a wonderful skill. Now we have to find, with the initial conditions, we have to find the real particular solution that we have. So my answer is going to be in the form y is equal to c1 e to the 3x plus c2 e to the minus 3x. And we're supposed to find out what c1 and c2 are. So that's first initial condition. We'll apply it. And we say, well, y at 0 is minus 1, which is going to be c1 plus c2. And then we're going to go and take the derivative. Y prime is going to be 3c1 e to the 3x minus 3c2 e to the minus 3x. And we're going to apply the second initial condition, which says y prime at 0 is 15. And that's going to be 3c1 plus minus 3c2. Okay. So now we're in our 9th grade algebra class with two equations to a nose. We have c1 plus c2 is equal to minus 1, and 3c1 minus 3c2 is equal to 15. And of course we would use Kramer's rule to solve this because any other way would be ridiculous. So c1 minus 1, 15, 1 minus 3 divided by 1, 3, 1 minus 3. On the bottom I got a minus 6. On the top I've got 18. 12. On the top I have 12. So C1 is going to be minus 2. Well, if C1's minus 2, then C1 had best be 1, right? C1 had best be 1. Times 3 is 6, plus 3 is 9. This is minus 12. That's a plus 2. If it's plus 2, if C1 plus 2, then C2 had best be minus 3. 6 plus 9 is 15, and 2 minus 3 is minus 1. Okay, so we finally solved that right. Okay, so now we can write down the final answer. Final answer. Y of x equals 2e minus 3 e to the minus 3x. Okay, so that's my final answer. Now, a final answer is no good unless we check it. So now we'll commence a checking thing. So we're going to check it. Y at 0 is supposed to be 0. No, it's not. It's supposed to be minus 1, right? It is minus 1. Check. Okay, so I got y of x, 2 e to the 3x minus 3 e to the minus 3x. I got y prime of x is 6 e to the 3x plus 9 e to the minus 3x. Y at 0 is supposed to be 15. Y at 0 is supposed to be 15. Check it is. Y double prime of x, 18 e to the 3x minus 27 e to the minus 3x. I'm supposed to have one of those and minus 9 of those, and when I get done, I'm supposed to have 0. Okay, so minus 18 plus 18 is 0. Plus 27 minus 27 is 0. 0 plus 0 is 0. So now I'm done. That is exactly what I'd expect to see on the next test. I expect you to get the problem and then check the problem. Now, why do we want to check the stupid problem for? Otherwise, other than waste paper. No. How do I know that? Well, there's 2 again. You wouldn't know which one to start about. If I put 1 plus 1 is 2 on the board, would you check your work? No, you wouldn't, right? No, you wouldn't. Why not? Because it's obvious. It's right, right? All right. But if I have a differential equation and I say that the answer is 43 hyperbolic sine x plus 15 hyperbolic cosine x, and you look at the problem, would you know whether or not that was right? There'd be no clue, right? You'd have no clue. You'd have to check. Right? And that's the issue. In differential equations, we left our comfort zone of being able to work a problem. So I'm going to throw the thing up in the air, and it comes down. And I made a calculation and said it was up in the air for 15 seconds. Is that right? No, it's not. So I don't have to check my work. I know what's wrong. I have to go back and recalculate, right? Yeah. So I have a feel what the right answer is. In differential equations, we have no feel. Looking at number 6.
Oh, what is Kramer's rule?
Kramer's rule?
Yeah. Like the actual, like...
Yeah, Kramer's rule says that if I have a1x plus b1y plus c1z is equal to d1, and a2x plus b2y plus c2z is equal to d2, and a3x plus b3y plus c3z is equal to d3, then x equals, on the bottom, a1, a2, a3, b1, b2, b3, c1, c2, c3, that's determinant. On the top, because I'm trying to find x, I'm going to substitute the a's with what's on the other side of the equal sign, d1, b2, b1, b2, b3, c1, c2, c3. So that's good. A 4 by 4 could be a 5 by 5, it could be a 10 by 10, which begs the issue, seeing that I just happen to have a Kramer's rule solver sitting in a program, and that's probably go in Office, Excel. So we'll get that program off, so these who are using it. I'll put it on the website.
negative 1 and 15, and that one, like, the negative 1 should be a negative 3, and the 0 and 9 should be a negative 1 and then 15.
I know you're doing a real good job trying to mumble to get me to use the right stuff. All right, so we come back to the original problem, and it's 1, 1 minus 1. Okay, so that's what it is. I have an Excel spreadsheet to solve those for you if you'd like. But you guys don't have graphing calculators, right? Yeah, and the graphing calculators, what do you mean you don't have graphing calculators? What kind of math majors are you guys? Anyway, so, yeah, so if you had a graphing calculator, you could put it in a graphing calculator. Back to number 6. So we're going to do the same thing over again. Y double prime, y prime, minus y, minus 6y is 0. Y1 e to the 2x, y2 e to the minus 3x. Give me y at 0 is 7, y at 0 is 7, y prime at 0 is something. Negative 1, right? All right, we'll go with that one. Okay, so now we're going to check to see that this is a solution. y1 prime, 2 e to the 2x, y2, y1 double prime, 4 e to the 2x. Okay, I got one of them, I got one of them, I have minus 6 of them. I'm supposed to have 0. Minus 6, minus 4, 0. Check. So that guy checks. Do the same thing over here, y2 prime minus 3 e to the minus 3x, y double prime 9 e to the minus 3x. I'm taking one of them, minus 6 of him. And when I get done, I'm supposed to have 0. So minus 6 minus 9 plus 9, 0, that solution checks. So that being the case, y of x is going to be in the form as a general solution c1 e to the 2x plus c2 e to the minus 3x. And now we have to solve for c1 and c2. So I go y at 0. Y at 0 is 7 is going to be c1 plus c2. Y prime of x is 2c1 e to the 2x minus 3c2 e to the minus 3x. And y prime at 0 is minus 1, which is going to be 2c1 minus 3c2. So I've got two equations, two unknowns. I have c1 plus c2 is equal to 7. I have two c1s minus 3 c2s equal to minus 1. And how are we going to write it down? c1, c2. Get them? And then I'm going to use Cramer's rule and say c1 is equal to, on the bottom I got 1, 1, 2 minus 3. On the top I have 7 minus 1, 1 minus 3. 3 minus 3 minus 2 minus 5 on the bottom. Minus 21 plus 1, positive 20 on the top. So it looks like we've got a 4. So C1 is going to be 4. if C1's 4, then C2 had better be 3. C2 had better be 3. Come back and check. 8 minus 9 minus 1, check. My final answer, 5x becomes 4 e to the 2x plus 3 e to the minus 3x. And now I'll start my checking again. So I'm checking again. And I'm saying y at 0 is 7, check. And then y is 4 e to the 2x plus 3 e to the minus 3x. My prime 8 e to the 2x minus 9 e to the minus 3x. I'm going to check the initial condition. Y prime at 0 is supposed to be minus 1. Check it is. Y double prime 16 e to the 2x plus 27 e to the minus 3x. I take one of those, and minus 6 of this guy, and I'm supposed to get 0. Okay, so I got minus 24 plus 24. Those guys go away. I got minus 18 minus another 9 plus 27. Those guys go away. 0, 0, 0, and I check. Oh, look at 16. Isn't that cool? What's so cool about 16 is that nowhere in the book do we have a method for solving that differential equation. But in chapter 2, it shows up there for us to check to see if it really is. That's what's so cool. So I've got number 16, x squared y double prime plus x y prime plus y. And I'm going to check my two solutions. Okay, so y1 is cosine of the natural log. Okay, so the cosine of the natural log of x. So y prime 1 is going to be 1 over x minus 1 over x sine the natural log of x. Y double prime 1. Oh, what is y double prime 1 going to be? It's going to be 1 over x squared over x squared sine natural log of x minus 1 over x squared minus is still there, so it'd be plus 1 over x squared. The derivative of minus sine is minus cosine, right? So the minus sign is still there. X squared cosine natural log x. Oh well, hope I did that right. So I'm going to have this times x squared times x times 1, and when I get done, I want to have 0. So that's, you know, someone somewhere said something about wanting. I'm not sure what it was. Okay, so I got a cosine there. I got a minus cosine there. I got a sine here, and I got a minus sine there. So 0 is equal to 0. That is, in fact, a solution to the differential equation. So given the ability to go and find those derivatives. Okay, y2 is sine of the natural log of x. So y prime 2 would be 1 over x cosine natural log of minus 1 over x squared cosine natural log of x minus 1 over x squared sine natural log of x. And a little bit of luck I did that right. I get one of those, I got one of those, I got one of those. When I get done, I want to have 0. Okay, so I've got a sine guy and I got a minus sine guy. They go away. I got a cosine guy, I got a minus cosine guy. They go away. The only thing I'm missing is a set of brackets. So that's fine. So 0 is equal to 0. It checks. So both of those are in fact what?
What the x squared?
What x squared?
The original formula was x squared.
Oh, I'm sorry. That's what I did.
Okay.
Did you notice that that's what I did?
How do you get the last line with the double prime part? I can see.
What? No compound? So the general solution would be C1 cosine natural log x plus C2 sine natural log x. And I have initial conditions that say y at 0 is equal to something. And y at 1 is 2, and y prime at 1 is minus 3. Now, I can't have y at 0 because I can't take the natural log of 0. That was a non-starter. Okay, so back to what we're doing here. Y at 0 is 2. The natural log of 1 is 0. The cosine of 0 is 1, C1, plus the natural log of 1 is 0. The sine of 0 is 0. So I'm done. And this is supposed to be 2. So this implies that C1 is equal to 2. C1 is equal to 1. So now I've got y is equal to cosine no one's complaining yet, but I'll erase it anyway. Okay, as I was saying, y at 0 is 2, which is equal to C1, implying C1 is equal to 2. Okay, because the sine guy went away, the cosine guy becomes a 1. Okay, so now I've got y is equal to 2 cosine natural log x plus C2 sine natural log x. And I'm going to take the first derivative of that y prime, and I'm going to get minus 2 over x sine natural log x plus C2 over x cosine natural log x. And y prime at 1 is supposed to be 3. This term is 0 again. I'm going to have C2 over 1 times 1, implying that C2 is equal to 3. And now I can write down my final answer. Y of x is equal to 2 cosine natural log x plus 3 sine natural log x. And then I would proceed to check my problem. derivative of pi would be 0. And squared, which is equal to 1. The derivative of 1 is 0. This is 0, so this is linearly dependent. I need to put cosine squared, sine squared there and do all that work? Oh, what a pain in the butt. All right, so I'll do that. Pi 0 cosine squared plus sine squared. So this will be 2. Cosine x sine x plus, no, that'd be minus 2 cosine x sine x. And then I take and that's a 0. So that becomes a 0 down there anyway. And it's still 0 as it was before. So everything is still 0. But there's no reason I have to, in differential equations I can be smart. I don't have to be. There's no requirement. Well, see that was so easy. Look at 42. Y double prime 35 90 y double prime minus 12y is equal to 0. Okay, so I have a characteristic equation. My characteristic equation is 35r squared minus r minus 12 is 0. That factors into r, 5r, and I had 3. I had plus 4 minus 3 is 0. Then I would come up with r is equal to solution set minus 4 over 7 and positive 3 over 5. And I'd have y of x is equal to c1 minus 4 over 7x plus c2 e to the over 5x. And I would be done. I would then grab out my green crayon and check my work. Y prime x equals minus 4 sevenths c1 e to the minus 4 sevenths x plus 3 fifths c2 e to the 3 fifths x. Y double prime x equals 16 over 49 c1 e to the minus 47 over x plus 9 over 25 c2 e to the 35x. Okay. And I want 35 of this guy. And minus 1 of that guy. Minus 12 of this guy. And when I get done, I best have 0. Okay, well, I guess at this point would be the right time to take out one's calculator, wouldn't it? But minus 12 plus 4 divided by 7 plus 35 times 16 divided by 49 equals. Okay, so those guys all cancel each other out. I got a 12 minus 3 plus 35 times 9 25ths also equal to 0. So those guys cancel each other out. This is a 0 check.
Can you go back up to the top a little bit?
Top of the entire problem? Did I make a mistake up high?
From like the 35 to the, is that an R squared or a pi?
That's an R.
So how do you?
So the characteristic equation, and the very first thing we did today, remember the very, well, not the very first thing, but remember the very first thing we did today? We said that if we were to have something like that, and it had solutions like that, we would get down to a characteristic equation that would be number R squared plus number R plus number is equal to 0. And then we would factor that characteristic equation. So I'm applying, yeah, I'm applying the fact that I have a characteristic equation. What is that doing there? That's pretty silly, isn't it? There, now it's in the right spot. So I'm saying that that differential equation has this characteristic equation, yes, directly.
And that's because it has the double prime, prime, and normal.
No, that's because the coefficients are all numbers. There's no x there, there's no y there.
So what if it was
That's
like,
why we do that.
what if it was like 35 y prime minus, okay, then it'd be x.
Yeah.
That's what you're saying.
What if I had something like y quadruple prime? Do one of these things real quick. So what if I had y quadruple prime plus 4y triple prime plus 6y double prime plus 4y prime plus y is equal to 0? What if I had that? Well, that would have a characteristic equation, and it would be r to the 4th plus 4r cubed plus 6r squared plus 4r plus 1 is equal to 0, and I would factor that r plus 1 times r plus 1 times r plus 1 times r plus 1, and I would say r has the quadruple root of 1, 1, 1, 1, and I would say y of x is equal to c1 e to the x plus c2x e to the x plus c3x squared e to the x plus c4x to the 4th e to the x. I would apply the characteristic equation the same way. Find the characteristic equation, I find the roots of the characteristic equation. Yes, you've never done this in your entire life. Isn't that what fun for you? And that's what differential equations are about doing things you've never done before. Isn't that way? Why am I bothering? Chapter 2, section 2. So 2-2. What we're going to deal with is something that's non-homogeneous. So if I have something that says y double prime, ay double prime plus by prime plus cy is equal to some f of x, some function, whatever it might be. Then what I'm going to do is I'm going to go find the characteristic equation of the homogeneous equation, a r squared plus br plus c is equal to 0. Find the roots of that, r1, r2, sub C is equal to the solution to the homogeneous equation, C1 e to the R1x plus C2 e to the R2x, or they could be imaginary numbers, or they could be repeating roots, whatever they are. And then I'm going to say, I've got a particular solution, y sub p, and it's going to be a f of x plus b f prime of x plus c f double prime of x plus blah, blah, blah. So it's going to be, the particular solution is going to be in the form of some constant times the forcing function plus some constant times the derivative of the function, forcing function, until I have all the derivatives. Now, if I have an infinite number of derivatives, I suppose, I have some other method to solve it. But if this were a sine, for example, sine x, then what are the derivatives of sine x? Or sine and cosine. So I would do that. I would then take the first derivative of the particular solution, and then I would take the second derivative of the particular solution, and then I'd say, well, I have, clearly I'm hosed because I have an A, B, C up there, and I have A's, B's, and C's across there. I'd take A of that guy, B of this guy, C of that guy, and then I would solve for those coefficients A, B, C, D, E, F, and things I have, and then after I do that, I'm going to say my answer is going to be whatever the homogeneous solution was plus whatever the particular solution was. Andrew, you have a question?
You answered it while you're talking.
Isn't that great?
Yeah,
Don't you just love that?
Is the YC for a characteristic equation?
You would think of it that way. I don't think of it that way. I think of it as the homogeneous solution. So why isn't it in Y of H? What does the author use? So it probably does in characteristic solution. But I've never heard that. I've never used that in my entire life. I have a very short life, so I'm only 67 years old. So that's not. Okay, so that's what we're going to do. I'm going to look at problem number 2. As a problem 126, show the likelihood given functions are linearly dependent on the. Well, that's just thinking for Wronskian. So we're not going to do that. Problem 7 through 12, use the Wronskian to prove that the given solutions are linearly independent. Number 14. Find the solution. Oh, we're given the solution. Again, we're not being allowed to find the solution yet. We're going to be given it. So that well, we'll do it differently. Y triple prime minus y prime plus 11 y prime and I've got that y 0 0 y prime 0 0 y double prime 0 is 3. That's what I have. Well, they gave us the solutions, right? But we'll find them. Well, we won't even look in the book. So I got a characteristic equation. It says r cubed minus 6r squared plus 11r minus 6 is equal to 0. Now, clearly, r is equal to 1 is the solution to that equation, right? So r equals 1 is the solution. So we're going to take r minus 1, divide it into r cubed minus 6r squared plus 11r minus 6. Okay, so it goes into r squared times squared minus r cubed minus r squared, I subtract, minus 5r squared plus 11r minus 6. Minus 5r. Minus 5r squared plus 5r. That goes away, that goes away. That's 6r minus 6 plus 6. And then that factors r plus, let's see, r minus 3, r minus 2, right? R minus 2. So that means my solutions will be 1, 2, and 3. And y of x is going to be c1 e to the x plus c2 e to the 2x plus c3 e to the 3x, which are the solutions they gave us, right? That's all fine. Now, I could check these guys one at a time, or I could go find C1, C2, C3, and then check it, and then everything would be checked at the same time. So that's my plan. Y at 0 is a 0, which is C1 plus C2 plus C3. Y prime x, C1 e to the x, 2 C2 e to the 2x, 3 C3 e to the 3x. Y prime at 0 is 0, C1 plus 2 C2 plus 3 C3. Y double prime x, C1 e to the x plus 4 C2 e to the 2x plus 9 C3 e to the 3x. Y 3 at 0 is 3. That doesn't look like 3, I think, is C1 plus 4 C2 plus 9 C3. Part of the board that we're not using, we will write that down so we don't forget it. So we got C1 plus C2 plus C3 is 0. C1 plus 2 C2 plus 3 C3. C1 plus 4 C2 plus 9. We could use Kramer's rule to solve those, or we could grab our spreadsheet. One is 0, 1, 2. Did I put those in right? And now, if you don't have a graphing calculator to put in your graphing calculator, then you'd have to do that by hand. So, C1 is 1.5, C2 was something, C3 is something, 1.5, and minus 3. Minus 3. So, the first guy works, the second guy, 6 works, the fourth guy, minus 12. So minus 1.5, so that's 10, 15, minus 12 is 3, so that's correct. So my final answer, y of x is 1.5 e to the x plus minus 3 e to the 2x plus 1.5 e to the 3x. And then I'd have to check my work to make sure it was right. I erased it for going to
When you did the last equation, how did you know that r equals 1 was the solution? Did you just guess?
You didn't know that? Really?
That's 2, 3.
Oh, my goodness. Several years ago. So the issue is, when I look at the equation, how can I tell one is a solution? I have minus 6 for 12. I've got an 11 and a 1 for 12. That's how I knew that. So if I didn't know that, if that wasn't a solution, what would be the next number I look at? First of all, I'm going to look plus or minus 1, right? But the, what is it, the remainder theorem, is that it? The remainder theorem says, if I'm going to have whole number answers to a quadratic formula, to a polynomial, any polynomial, that those numbers are going to be factors of the unit coefficient. Okay, so plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6 would be the only whole number answers to a polynomial that ends with minus 6. If any exists at all, those are the only ones that it could be.
That's only if the highest exponent doesn't have a
No,
coefficient.
doesn't matter.
Doesn't matter.
This could be r to the 15 millionth, and I've got a whole shit pile of them. It doesn't matter. So it could be r to the 10th, minus 6,
Well,
r to
there's
the
a coefficient
9.
in front of this. Does it have to be 1?
No.
It doesn't?
Oh,
The
yeah.
coefficient,
If this wasn't 1,
then you have to make it 1.
no. No. If this isn't 1, then it's the factors of this guy plus all the factors of that guy divided by all the factors of that guy. Of course, with a different color. That's the part that they get on the test. So normally what's going to happen is visually I look at it, well, one's an answer. Well, if one's an answer, now I can figure out what the other two are because I only have a quadratic value. If one wasn't an answer, then minus 1 may have been, or plus or minus 2. Run those through my head real quick. So that's how I knew. It wasn't like I looked at this in advance or anything. I don't show that, right, that I looked at this in advance. We're going to do problem number 24. Y double prime y is equal to 2x. So I have a characteristic equation of a homogeneous problem. That means it ends in 0. And it's r squared minus 2 plus 2 is equal to 0. And that factor is, is that really a problem? doesn't factor. So r, we're going to use quadratic formula. So r is going to be minus 1 plus or minus the square root of 1 minus 2 divided by 1. Okay, so we got minus 1 plus or minus I. Okay, so y sub c is going to be times c1 cosine x plus c2 sine x. So anything to say about that, Andrew, or can I continue? Pull the fast one. Can I pull a fast one? If I pull the fast, yeah, the first time I saw that, I was in a complex variable class, and my hand went shooting up in the air, and I was telling the professor that it's pull it. And he explained to me that if you have a quadratic equation, a x squared plus bx plus c is equal to 0, then x is going to be minus b plus or minus the square root of b squared minus 4ac divided by 2a, and you guys would say, well, you mad brother, that's right. How come you didn't do that, Porterville? What's wrong with you? Okay. You would say that, right? Yeah. But no, I did something different. I pulled the wool over your eyes, right? Well, consider for an equation that looks like ax squared plus 2bx plus c is equal to 0 for a moment. And then we'll find that x is equal to minus 2b plus or minus the square root of 2b squared minus 4ac divided by 2a, right? Same thing you have up there. But now I've got a 4 sitting here. I got a 4 sitting there. I can factor out that 4. That 4 comes over here is now a 2. I got a 2 there, I got a 2 there, I got a 2 here. And now this guy becomes x is equal to minus b plus or minus the square root of b squared minus ac divided by a. And how many times in your adult life, or your child life, depending on how old you are, have you executed quadratic formula and got the wrong answer? Yeah, if I told you that every time this was an even number, you could do less operations and get the right answer, wouldn't that have been cool?
So is it anytime there's a 2 there?
Anytime this is an even number, this is called the half quadratic formula. Yeah, no one in the math department would tell you about it. That's why I'm the electrical engineering guy. But that's what I used. I saw that I had an equation sitting there with a 2 sitting there. And instead of putting a minus 2, I put a minus 1. Okay, because this is now 2b. So minus b plus or minus the square root of b squared minus ac divided by a.
So if it was a 4, would there just be like a plus or minus 2 instead
So
of square
if
root?
this were a 4, then I'd go minus 2 plus or minus the square root of minus 2 squared minus 2. Yeah. So whenever I have an even number sitting there, I use the half quadratic formula, and I don't make as many mistakes that way because my calculation isn't as good. Okay, isn't that nice? But no one's going to teach you that in 10th grade because they want you to get the wrong answer and be able to mark things off. All right, now we have to look at our y sub p. Y sub p is equal to ax plus b. So I look at my forcing function, it's 2x, so it's going to be a function, some coefficient in x, plus that derivative, which is just a constant. Okay? And then I say, well, that being the case, y prime p is a, y double prime p is 0. And my equation is minus 2 of those, and 2 of those have to be 2x. Now, in this particular problem, I don't have to do this, they've already done the formula. So I've got 2ax plus 2b minus 2a. It has to be 2x. Now, what that means is that my unit term is 0. There's no 0 over here. So 0 has to equal 2b minus 2a. My x term has to be a 2. So 2a has to equal 2, implying that a is 1. If a is 1, then b is 1. Which implies b is equal to 1. So my particular solution implies that p is going to be x plus 1. My final answer, y of x is equal to minus x. We'll call it c1 e to the minus x cosine x plus c2 e to the minus x sine x plus x plus 1. That would be my final answer. And if I look, that's the answer again, right? So c1 minus x, and I have e to the x. The minus, oh, wait a minute. This is minus minus, so that makes that plus, that makes that plus. And no one caught me on that one. No one counted as wrong, I just corrected. X and X. Now I've got to check my work. All right, so I got y of x, c1. Do I have initial conditions? Oh, bummer, I got to solve for the initial conditions yet. Okay, so y at 0 is 4. So this is not a final answer. Get rid of that. Y at 0 is 4. Okay, so that's going to be c1 plus 1 is going to be 4, implying that c1 is equal to 3. Okay, so y of x is now 3 e to the x cosine x plus c2 e to the x sine x plus x plus 1. Okay, y prime of x is equal to 3 e to the x cosine x minus 3 e to the x sine x and plus c2 e to the x sine x plus c2 e to the x cosine x plus 1. And y prime at 0 is which is going to be 3 from that guy, plus c2 plus 1, implying c2 is equal to 4. Now I can write down a final answer. Y of x equals e to the x cosine x plus 4 e to the x sine x plus x plus 1. And it's from there that I would check my work. plenty of time to check my work. Well, maybe we do, I don't know. So we'll rewrite, I'll write it down again. 3 e to the x cosine, 4 e to the x sine, plus x plus 1. I got y, 3 e to the x cosine, minus 3 e to the x sine, plus 4 e to the x sine, plus 4 e to the x cosine, plus 1. And y, 3 cosine, minus 3 e to the x sine, minus 3 e to the x sine, plus, minus 3 e to the x cosine, plus 4 e to the x sine, plus 4 e to the x cosine. Am I done? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We still have that one to do. All right. Plus 4 e to the x cosine minus 4 e to the x sine. All right. Now I got enough of them. And when I get done, I'm supposed to have 2x. That's what I'm supposed to have. All right. Anybody remember the original equation? So I got 6 cosine, I got minus 6 cosine. I got 8 sine, I got minus 8 sine. So they go. I got minus 2, so they go away. I got a 2x sitting right there. 2x. Now I can get rid of everything else. I would be happy. Okay, so now I've got minus 6 sine. I got positive. I got positive 6 sine, and I have minus 6 sine sitting there. I've got minus 8 cosine, minus 8 cosine. We have a plus 8, and I got a plus 8 cosine sitting right there. I got a plus 3 minus 3 cosine sitting there. I got a plus 4 minus 4 sine sitting there. And my work checks. Any questions?
How did you get the particular solution when you first did that? Y equals ax plus b.
Okay, so the forcing function
Right.
is 2x. So my particular solution has to be in the form of that function plus all the derivatives of that function. Okay, so that's the form I'm looking for. So my form has to be ax plus, what's the first derivative of x? Well, it's 1, so that'd be another constant.
So if it was like 2x squared,
Yes.
it'd be ax squared plus bx plus c.
So if it was equal to sine x plus x cubed, if that's what was there. Okay, so my particular solution would be in the form a x cubed plus b plus c x plus f cosine x. If you what a, b, D, E, and F are in order to make it work. What if my forcing function was tangent x? Opposed, right? Because I can't find all the derivatives in tangent x. I have an infinite number of them. Or what if I secant x, or cosecant x, or cotangent x? Well, toward the end of chapter 2, we have another method that we're going to use where my
The sign part, how come you only have to go because they're just repeated by that, but
Yeah.
negative pi?
Yeah.
Yeah.
because the sine of x and minus the sine of x are not really independent. They're the same guy. We are done for today. Isn't that great? Now I got to figure out how to turn this thing off.